What's up guys, it's Simon Fiaz and today's video is on AQA Level Chemistry Paper 1, June 2017. It's just a quick review. Obviously I'm not going through in detail every question, so it's probably going to be like a 5, maybe 10 minute video, probably 5 minutes long. So question 1, 1.1, define the term enthalpy of lattice formation. The idea that it's a standard enthalpy change when 1 mole of solid ionic compound is formed from its gaseous ions. 1 mole of solid ionic compound is formed from its gaseous ions. Then 1.2, use this data to calculate enthalpy of lattice formation of silver iodide. So you've got AgI solid, the aqueous ions, and then the gaseous ions, and you just need to know how to construct it. So I want to find out the enthalpy of lattice formation of silver iodide. So what do I want to find out? Enthalpy of lattice formation. So forming this silver iodide, so it's going to be 112 to go from AgI solid to here, plus X equals minus 464 minus 293, and then you should get X is equal to minus 869 kilojoules per mole to power minus 1. It's very important that you clearly indicates negative, obviously. Then 1.3 says the calculation of enthalpy of lattice formation of silver iodide based on a perfect ionic model gives a smaller numerical value than the value expected in question 1.2. Explain the difference. The idea that the perfect ionic model assumption is that ions are completely spherical, whereas the silver iodide contains some covalent character. And then don't just say that, because then say silver iodide contains some covalent character, therefore the forces holding the lattice together are stronger. Contains some covalent character, therefore forces holding the lattice together are stronger. Then it says identify reagent accused to indicate the presence of iodide ions in aqueous solution and describe the observation made. AgNO3, yellow precipitate. That's just how well you know your practical skills, all those tests for functional groups and all of that. Question 2, question about Ka, acid dissociation constant. Calculate concentration of ethanoic acid in the buffer solutions. I want to find out the concentration of this. First thing I do, rearrange this equation. Rearrange it, I get this. Then I know the pH is that. There's a reason they've given me that, because they want me to use it. Calculate concentration H plus, 10 to the power minus pH, 10 to the power minus 3.7. Then I substitute that in, and then I'm like, okay, concentration ethanoic ions, methane, ethane, this is minus. So ethanoic ions, it gives me that. I don't need to, sometimes what they like to do in these questions is they'll give you the information you need, but because students, including myself, are so used to finding out the moles and finding out the concentration that they just ignore it and they just think it's something else. No, that's the answer. That's the value they've given you, so use that. Use that. Ka is already giving you that. And then you get the concentration of the ethanoic acid, 1.05. So 3 marks are basically using this concentration H plus 10 to the power minus pH, then rearranging the equation, and you're finding out your answer. Question 2.2, in the different buffer solution, the concentration ethanoic acid was that, and the concentration ethanoic ions was that. This much of sodium hydroxide was added to this much of buffer solution. Calculate pH of buffer solution after the sodium hydroxide was added. Give your answer to 2 decimal places for 6 marks. So first thing we do is calculate the number of moles of your HA and your OH minus. So the number of moles of your HA in this case can be 0.26. That's the concentration times by the volume, which I know 500 centimeters cubed. 500 centimeters cubed, I want it moles per liter minus cube. Do that. Then find out the moles of your OH minus, so the ethanoic ions. No, sorry, that's the A minus, yeah. So find out the moles of that, 0.121 times by 0.5. Then you use this equation, right? And then you get the moles of HA, A minus. Then what you need to do is rearrange the equation to find out the concentration of H plus. Because remember, Ka is the concentration of H plus times by concentration A minus divided by HA. Rearrange it to find out concentration of H plus. Then you use pH as minus log 10 H plus, and then remember, give your answer to 2 decimal places. They may even deduct a mark probably if you don't give it to 2 decimal places. Then it says question 3, which is the correct expression for kW? Well, this is a very, very easy question. You know, the first time you look at kW, you're obviously going to look at the expression. It's the C, concentration H plus times by concentration OH minus. Then it says calculate the pH of pure water at 10 degrees Celsius. Now this one is easy, but it's, have you even been exposed to this type of question before? It's pure water, so I'm going to say concentration H plus equals concentration OH minus, therefore Kw equals concentration H plus squared, therefore concentration H plus is the square root of Kw. I know the Kw at 10 degrees Celsius is 2.93 times by 10 to the power minus 15. Substitute that in, and then use pH in minus log 10 H plus to find out the pH 2 decimal places. Then it says suggest why this pure water at 10 degrees Celsius is not alkaline. It's because the concentration H plus equals concentration OH minus, therefore pure water is neutral. If you just put that expression, you'll get the mark. Concentration H plus equals concentration OH minus. That's how specific it is. It just wants that. I'll give you the mark. Then 3.4, calculate the pH of this much solution of calcium hydroxide. Now, this is a trick. This is a trick to this part. So firstly, I'll write the Kw expression. I'm like, okay, I want to find pH, so I need concentration H plus ions. Rearrange it. Kw, I have got 2.93 times by 10 to the power minus 15. OH minus, well, calcium hydroxide, Ca bracket OH squared. So I've got 2 hydroxide ions. Therefore, it's going to be 0.0131 times by 2. Then I get the concentration H plus, and then I use pH equals minus log 10 to concentration H plus to find out the pH. And remember, give your answer to 2 decimal places. 3.5. This 0.0131 moles per d minus cubic calcium hydroxide solution at 10 degrees Celsius with saturated solution. Shouldn't add this much and stir the mixture until one more solid dissolved. Predict whether the pH of magnesium hydroxide solution formed at this much is larger than, smaller than, or the same as the pH of calcium hydroxide solution at 10 degrees Celsius. Explain your answer. pH of magnesium hydroxide compared to calcium hydroxide. I wrote same as both have the same moles of. Yeah, that's wrong. It's it decreases, I'm pretty sure, but the reason being is that magnesium hydroxide is sparingly insoluble. Is very, very sparingly soluble. Yeah, so that's that part. Then question 4, calculate relative atomic mass of titanium in the sample. Again, this one, 46 times by 9.1 plus this times by this plus this times by this plus this times by this over 100. And always double check, does the abundance always add up to 100? Sometimes it doesn't, because sometimes I'm pretty sure they don't give you any percentages. I'm not sure, but yeah, make sure it adds up to 100. Then it says write an equation to show an atom of titanium ionized by electron impact. So titanium gaseous to Ti plus gaseous plus E minus. MZ value that would reach the detector first, the one with the lowest MZ value, therefore 46. Calculate the mass in kilograms of one atom of this. Well, first things first, calculate the mass of one atom of this. I'm going to do 49. What I should have done is 49 divided by 6.022 times by 10 to the power 23, and then divide my answer by 1,000. But I guess this works as well, and you get 8.14 times by 10 to the power minus 6 kg. Question 4.4. Calculate the time of flight of the 47 Ti plus ion. So, I know the kinetic energy is that, time of flight is that. First thing I'm going to do, velocity distance divided by time. Distance is velocity times by time. Velocity is distance divided by time. Velocity is square root 2ke divided by m. Yes. I want to find out of the 47 Ti plus ion or not. No, because the 47 Ti plus ion doesn't have a time, does it? Okay, perfect. So I've used velocity square root of 2ke divided by m. 2 kinetic energies there. the mass of the 49 Ti plus ion, same method as it did in 4.3, 49 divided by 1000 divided by 6.022 times by 10 to the power 23, or 49 divided by 6.022 times by 10 to the power 23, then divided by 1000, because sometimes when you calculate, it doesn't give the correct value. Then you get the velocity, then you rearrange the equation to find out the distance of the flight tube, the velocity, which you just worked out, times by the time, which you've already got in the question. Then you've got the distance. Then I want to find out the time of flight of the 47 Ti plus ion. Well, how would I do that? Well, am I going to use distance and velocity times by time? No, I'm not going to use that. What I'm going to use instead is the idea that distance is time is the distance square root of mass over 2ke. So the distance I've got now, the flight tube, which is the same for both the 47 Ti plus ion and the 49 Ti plus ion. I've got the distance here. I'll put it here. The mass of the 47 Ti plus ion, 47 divided by 6.022 times by 10 to the power 23 divided by 1000, and then the 2ke, just 2 times by the kinetic energy, and then you get the time as that. Question 5.1, use the equation and data in table 3 to calculate Gibbs free energy change and then explain why this reaction is feasible. So, Gibbs free energy change, you have to recall the equation. Delta G is delta H minus T delta S. I need to find, I've already given delta H, so I need to use delta S is delta S of products minus delta S of reactants. Use that. Use the information given in table 3. And remember the number of moles. If it's got 2 moles, you times it by 2, whatever this is. You get delta S as 141.4. And that's measured in joules. Now I want delta G. Well, delta G is delta H minus 60 measured in kilojoules minus the temperature. Well, I want it in Kelvin, so 989 plus 273, that's in degrees Celsius to Kelvin at 273. And then delta S, well, I want my final answer kilojoules multiplied minus 1. Delta S is measured in joules, so I need to divide it by 1000. So 10 by 10 to the power minus 3, I should put it there as well. And then you get Gibbs free energy change as that, but I'm pretty sure, yeah, then you divide by 1000. And then whether the reaction is feasible, yes, the reaction is feasible / spontaneous as delta G is less than 0, delta G is negative. That's it for question 5. Question 6, write the equation for the reaction of phosphorus with the excess of oxygen. Phosphorus, I got confused between phosphorus oxide and oxygen. But yeah, phosphorus excess of oxygen, P4 plus 5O2 to form P4O10. They always like to ask this equation. Like I think at least maybe 3 times over all the past papers I've gone through that they love to ask this equation. So if any equation I would memorize from period 3 elements in the oxide, it would be this one if I was just going to memorize one. Then question 6.2, describe a test to distinguish between sodium oxide and the product of the reaction in question 6.1. Sodium oxide and the product in question 6.1, phosphorus oxide. So, sodium oxide and phosphorus oxide. So add water, add litmus paper. With the litmus is blue with sodium oxide solution. Yeah. And red with phosphorus oxide solution. Then it says state the type of crystal structure shown in silicon dioxide and sulfur trioxide. Silicon dioxide, you should know, giant covalent / macromolecular. Sulfur trioxide, maybe a bit more difficult, molecular / simple molecule, but yeah. Then it says explain why silicon dioxide has a higher melting point than sulfur trioxide. Silicon dioxide has a macromolecular / giant covalent structure, therefore has many strong covalent bonds between molecules, which requires a large amount of energy to break bonds. Whereas sulfur dioxide has weak van der Waals forces between molecules, which require little to no energy to overcome. Therefore, silicon dioxide has a high melting point than sulfur trioxide. These questions explain why something has a high melting point to this. 4 marks. These are the type of marks you 100% want to be guaranteeing. Like you've got 4 out of 4, because these are very specific to the mark scheme, and once you practice enough of them, they're very easy marks. Question 6.5, sulfur dioxide, potassium hydroxide, SO3 plus KOH to form KHSO4. Round equation for the reaction of excess of magnesium oxide with phosphoric acid, 3MgO plus 2H3PO4 to form Mg3PO4 2 plus 3H2O, and then draw the displayed formula of the undissociated acid formed when sulfur dioxide reacts with water. That but that sulfur has a lone pair of electrons on it. Question 7 I can't do. Question 8, describe how a student could distinguish between aqueous solution potassium nitrate and potassium sulfate. Now sulfate's got sulfate ions, so barium chloride with potassium nitrate, no visible reaction, potassium sulfate, white precipitate. Describe a student could distinguish between aqueous solution magnesium chloride and aluminium chloride, sodium hydroxide, white precipitate / white solid with magnesium chloride, white precipitate which dissolves in excess NaOH with aluminium chloride. Question 9. Deduce the optimum conditions for the industrial conversion of methane and steam into gaseous products. 6 marks. So I'm going to have 3 stages. Stage 1, the deduction from the graph. I can see that yield increases as temperature increases. However, after a certain temperature, yield no longer increases. Yield decreases, however, as pressure increases. So that increases, that's going down. Stage 2, the optimum temperature. While high temperature results in a high energy cost, therefore it's going to be expensive. However, after a certain temperature, the yield no longer increases, therefore there's no gain in using a high temperature. If the yield's not going to increase, why would we even use a high temperature then? So the optimum temperature is between, just interpret from the graph, 780 to 880 degrees Celsius. Stage 3, the optimum pressure. Well, low pressure, if we use a very, very low pressure, well, the 1000 kilopascals is going to be too slow. So compromised pressure is required. Therefore, optimum pressure is between 1000 to 2000 kilopascals. Remember, 2000 kilopascals. Question 9.2. Calculate moles of carbon monoxide and of hydrogen in equilibrium mixture. Use the method that I like to use, ICE method, initial moles, change of moles, equilibrium moles, carbon monoxide, hydrogen, and methanol. Then I've got 20.1, given a question, 24.2, and then equilibrium mixture, equilibrium moles 2.16. So I've added 2.16 and minus 2.16. But in this case, because I've got 2 moles of that and a 1 and 1, I'm going to minus 2.16 times by 2. And then you get equilibrium moles of carbon monoxide and of hydrogen. And then question 9.3, calculate value for equilibrium constant Kp for this reaction at 600 Kelvin and state its units. Now, don't be intimidated by the fact that it's 6 marks. That's probably my biggest advice I would give. Don't be intimidated, because as soon as you're intimidated, you're going to overreact and then think that there's more steps than necessary. And then if you do get the correct answer, you'll probably cross it out because you're like, this can't be too easy. You know what I mean? Happens to me as well. A lot of times, actually. So firstly, construct the Kp expression. And then realize I'm given the equilibrium moles of all of this, find out total equilibrium moles. Then realize, okay, well, now I need to find out the mole fraction. So equilibrium moles over the total equilibrium moles. Then I'm going to times by the total pressure, 630 kilopascals. So this is not actually the mole fraction. This is the partial pressures. The mole fraction times by the total pressure for each one. Then realize hydrogen squared. Substitute the values in for the partial pressures. You get Kp and the units. Well, because I've got pressures kilopascals and kilopascals squared over kilopascals cubed over kilopascals, I get kilopascals squared, and Kp just like that. And that's that question done. Question 10 I can't do. Question 11, calculate the percentage by mass of sodium ethanoate by solid, give you answers appropriate and significant figures. Now, in my opinion, this is the hardest type of math questions or mathematical questions they could ask you. These calculation questions involving back titrations, in my opinion, not the hardest. And you just got to get a highlighter, highlight not every, but the key thing you're going to be needing to use. Find out the moles firstly. So moles of this, using information given, get that. Moles of this. Well, because I've got a 2 to 5 molar ratio, then I'm going to turn by 5 over 2 to get the moles of this. Then to find out the moles of sodium hydroxide, the OH minus ions, I do that and I get that. Then the moles of Cr2O42 minus from the acid, well, that divided by 2, get that. And then the moles of C2O42 minus is going to be 1.325 times by 10 to the power minus 3 minus what I just worked out, that to get that. Then the moles in the original sample I was working with originally 250 centimeters cubed, but in the titration I was doing 25, so I need to times by 10. times by 10 to get 8.025 times by 10 to the power minus 3, and then therefore to find the mass of that, moles of mass or MR, mass is moles times by MR. You get the mass, and then you substitute that over the total mass 1.90 of the solid times by 100 to get 56.6%. And that's 8 marks for that question. 11.2 can't do. 11.3, yeah, can't draw the displayed formula iron complex. I'm going through complexes, but the bond angle is 90 degrees Celsius, type of isomerism, optical isomerism. Then it says, suggest one reason why people who eat these foods do not suffer from poisoning. And it says it's poisonous because they react with ions in the body and are present in foods such as broccoli and spinach. The idea that ethane dioic acid is only present in small quantities / low concentration in these foods.